So, let us begin. Before we start looking at equipment in detail, we should first of all review some basic fundamentals. Now, I know that many of you are already familiar with this material, but please stick with us. It's going to get more interesting as we go along. First, we'll look at the standard gas turbines, and in later videotapes, we'll study some of the more advanced machines which are currently under development. The gas turbine is actually an internal combustion engine. It is, in fact, often called a combustion turbine. It burns a very lean mixture of fuel and compressed air. We could easily think of this as a hot air machine, since the gas passing through the turbine consists mainly of air, plus some products of combustion mixed in. Of course, air is also a gas, so the term gas turbine is quite correct. In the turbine, hot pressurized gas passes through a series of stationary and moving turbine blades, and this causes rotation of the shaft. The hot gas expands as it passes through the turbine, and this brings about a drop in temperature and pressure. The gas has given up heat energy and converted this to mechanical energy in the turbine. The gas is finally exhausted to atmosphere. And for this reason, this process is known as the open or simple cycle gas turbine. There are other cycles, as we'll see. In this basic gas turbine, there are actually four processes that take place. That is, compression in the compressor, heat addition in the combustion chambers, expansion through the turbine, exhaust to atmosphere where heat is lost. In order to help us get a better feel for the operation of the unit, let's consider some typical values of pressure and temperature. To begin the cycle, air is drawn in from atmosphere through an air filter into the compressor. As the air passes through the compressor, pressure is raised. The compression ratio depends upon the particular design of turbine. Where the pressure ratio is, say, 10:1, the pressure of the air as it leaves the compressor is 10 atmospheres. That is about 147 psia, 1,035 kilopascals, or 10.35 bar for you metric types. The temperature of the air will also rise as it is compressed, typically to about 450 degrees Fahrenheit, that is 230 degrees Celsius. The compressed air is routed into the combustion section, where it's mixed with incoming fuel. The fuel may be oil or natural gas or even gasified coal in some instances. We'll be discussing fuels in greater detail later. When the machine is first started up, the fuel must be ignited by a spark plug or some other form of ignition. However, once combustion is established, it will continue until the fuel is shut off. As a result of combustion, the temperature of the gas entering the turbine is raised to, say, 1,800 degrees Fahrenheit or 980 degrees Celsius. On large, modern machines, the turbine inlet gas temperature may be as high as 2,400 degrees Fahrenheit, say 1,300 degrees Celsius. Obviously, the temperature of gas entering the turbine increases when the amount of fuel supplied to the turbine is increased to accommodate a load increase. As the gas passes through the turbine, the temperature and pressure fall as energy is given up to the turbine to perform mechanical work. The turbine shaft is coupled to drive a load such as an electric generator. Eventually, the gas discharges at close to atmospheric pressure and a temperature of, say, 1,000 degrees Fahrenheit or 537 degrees Celsius. Now, please bear in mind that the values we have chosen are merely an example to give us a feel for the order of magnitude. When you're working with gas turbines, make sure that you know the specific figures related to your particular machine. You will often see this simple cycle represented on a diagram like this. It's called the Brayton cycle, after one of the inventors. The vertical axis represents temperature, and the horizontal axis is related to the addition or extraction of heat. At point A, air is drawn into the compressor. It is compressed and the temperature rises, although no heat is added from an external source. At point B, fuel is added and combustion takes place. As we would expect, the gas temperature rises while heat is being added. From point C, the gas enters the turbine and expands. The heat energy is converted into mechanical energy until point D, where the gas is exhausted to atmosphere. All of the remaining heat in the gas is lost to atmosphere until the cycle begins again at point A. The efficiency of the Brayton cycle depends very much upon the pressure ratio. That is, the ratio between the pressure of air leaving the compressor and the air entering. You'll see from this curve that with a 10-to-1 ratio, the cycle efficiency is about 50%. One thing we have to remember is that the compressor absorbs a large amount of energy. For example, in a typical gas turbine, approximately 50 to 65% of its output may be used to drive the compressor. On most large gas turbines used for power generation, the compressor is mounted on the same shaft as the turbine. However, on smaller units, it's quite common to have a two-shaft arrangement. In this machine, both the compressor and the generator are driven by separate turbines. This has a certain advantage as it allows the compressor to run at much higher speed, where greater efficiency may be obtained. Both of the gas turbines are in the same gas flow path. Typically, the gas would pass first through the compressor turbine and then through the power generation turbine. We have already noted that the exhaust gas leaving the turbine contains a lot of heat. In order to recover some of this heat, a heat recovery steam generator may be placed in the gas passage. The aim is to lower the gas exhaust temperature to about 500 degrees Fahrenheit or lower if possible, and produce steam in the process. This steam, typically in the range of 100 to 1,000 psi, can then be used for industrial purposes, district heating, or some other heating requirements. In the combined cycle, the steam is used to drive a steam turbine generator. Typically, we may have, say, two 100-megawatt gas turbine generators providing exhaust heat to run one 100-megawatt steam turbine generator. The advantage of this arrangement is that the overall efficiency, that is, electrical energy out compared with heat energy in, is higher than either the standard steam turbine cycle or the gas turbine cycle alone. The combined cycle also offers an economic gain. The capital cost of installing a gas turbine generator is much less than the equivalent steam turbine installation with its associated boiler and auxiliary plant. Yet another advantage is that the gas turbine can be installed and be available for operation in far less time than the conventional steam plant. So you can see many reasons why power companies are currently installing gas turbines and combined cycles.